All right, guess we're at the time. Hi, everybody. My name is Mike Bassett. I'm program manager from Fast Track Engineering, Microsoft. Got Jim Matala over here. He's HP solutions engineer, and Anjan Das. He's our marketing representative here today. Today, just so you know, you're in the right room. Fast Track V3. Talking about the new features and best practices. I don't know how many of you guys know. Raise your hand if you actually have heard of Fast Track before, or V2, or there you go. Has anyone used it before? V2 Fast Track? So you guys have. All right, great. Successful program here. Let's go. Quick agenda. We'll talk about what we're going to talk about, some reference configurations, the best practices. Jim will get more into the new features, specifically with HP. Obviously, Fast Track, for those of you who don't know, Fast Track is about reference configurations, general Fast Track recommendations. Specifically, as you can see here, it's trying to recreate expected performance, predictable performance. We focus on a workload, on a specific workload, data warehouse workload. Deployment of the balanced hardware database configuration for a data warehouse workload. Now, what is a data warehouse workload? We'll get to that in a second. Right now, what we want is a predetermined balanced configuration, predetermined performance, eliminating the risk of overspending for CPU, overspending for disk. The old experience with SQL Server, you're not getting enough of performance. You buy a bigger server. You buy one of those big guys right over there. And you still don't get enough performance because you don't have enough disk. You don't want to overspend that way. You can do the same thing and spend too much on disk, and your CPUs are your bottleneck. You're not getting your performance. So to get predictable out-of-box performance, we've come up with a way to build Fast Track configurations, build reference architectures that are balanced, that are already pre-configured. We give you the hardware to buy, the bill of materials, exactly what to do, and exactly how to configure them. To get your best experience for a data warehouse workload. Now again, I keep saying workload. This is a workload-centric solution. This is not something you're going to want to do for OLTP. It's not something you're going to want to do for more of a mixed workload. Rather than be one-size-fits-all approach, this is specifically data warehouse workload. Now workload evaluation for this workload involves a scan-centric evaluation. The data warehouse is big data, big tables, aggregations, not volatile. We don't want to use indexes, something we could use partitioning for, range partitioning. Not going to do a lot of transactions, not going to do a lot of small requests. That's why we don't need indexes. We need to do big, large scans. That's why we've designed the architecture to be able to do those scans as efficient as possible. Random I/O is something that's not appreciated in data warehouse workload. We want to get something more scan-centric, more sequential in its in I/O performance. The key to that is involved with the best practice. The methodology for loading your data warehouse involves minimizing fragmentation, this logical fragmentation, to get the best performance scan. It minimizes disk head movement. You get a high average request size. You think of the 400K range, not the 8K range. It applies low IOPS. OLTP, it's all about IOPS. In this place, in data warehouse, or traditionally, we're looking at for large scan rates, sustain high average scan rates at 200 megabytes per second for RAID 10 LUN. That's just an example. Obviously, depends on the actual specific architecture that you're using and the drives and all the key features. Considerations, like I said, your methodologies are just as important as your hardware architecture. So laying the data, creating the right table structures, your right file groups, right partitioning, your format of the data, the size of the data, the CPU, the memory, everything comes into play. So that's all important. The entire program covers all these areas. So new methodologies for Fast Track V3. It's all about reducing load times and an initial load methodology for staging data, tables in final database. We start with the bulk copy. A quick example for a migration load, if you want to migrate 5 terabytes of data, you can't just throw it all in there and do a regular straight load back into your table. You want to avoid logging. You want to avoid lots of sorts. You want to avoid all those things in your database that slows everything down and kills you. So a quick example here: we do a BCP, we do a bulk copy into a heap table in staging database, and then we do an insert select from that heap table into small staging tables in the final database, to prepare it to build a clustered index to push into your final table with final partition switch. This avoids logging. This avoids too many sorts because your insert select is really just filtering data out. These methods that I'll go to in more detail, obviously, they reduce load times by as much as 50%. This is up from Fast Track 2.0, where we were a little bit more generalized in saying, throw your data in there, try to avoid fragmentation. The Fast Track v3 reference guide goes in much more detail about how do you do that? What are the best practices? What are the methodologies? Quick example here. Again, I just spoke of the migration load. Looking up here, we've got 6 file groups separated by 2 stage file groups, stage A and stage B, and we've split our table. Think of our big, for example, a line item table, partition across all these file groups. Notice how we've laid partitions on every file group. This way, if we are writing to one of those partitions and then we want to write to another partition, if they're in the same file group, they'll write at the same time. They're trying to get data into the same place at the same time. Thus, they'll start to fragment their actual data. They'll still put a little bit here, put a little bit from that partition there. But if you're in separate file groups, you can actually write to both those locations at the same time without creating fragmentation. Now, you see here we also have 2 partitions per file group. So if we wanted to actually make it as flexible as possible, we could do 8 different file groups for all the partitions. However, overlapping is easier to manage, right? You'll have less file groups to manage. But in this case, we don't want to actually insert data into all of them at the same time. We'd want to maybe do 1, 3, 5, and 7, and then 2, 4, 6, and 8 at the same time. Again, this is one big table. These are all separate partitions. Our example of source data, didn't jump to the next part. Coming from 8 data source files, our example here, pushes into, with an 8-core server, we can use 8 files, 8 processes at the same time. We're using all that CPU. However, we're pushing only into our stage file group. Just our stage base table. It's a heap table. We don't have to worry about fragmentation. It's just for staging. We dump it all in there. It goes as fast as we can. It's all, just slam down, table lock because it's an empty table. You don't have to worry about logging as fast as possible. From that point, we move on to actually separating the data, repartitioning the data. But instead of doing it with big sort, which takes lots of memory and lots of resources, you can do it with separate selects into separate 8 heap tables, stage heap tables. Now, my example here has 3 heap tables. That's just for the sake of having space on the screen to put stuff up there. Really imagine 8 heap tables right there. Simple select statements into all those tables. Doing that, it's just basically filtering the table. With each select, it's just a filter. It's not doing a sort. Much faster, much more efficient. Third step is transforming the data, putting it into a clustered index, just doing a build clustered index and defining it onto a different file group. We've moved the data, we've sorted those individual files at the same time, and we can do it all concurrently without creating too much sorts. We can fit it all into memory. It gets ultimately more efficient. Last bit is just switching the data into the final table. Small tables into the final partitions. It's switched in. It's just a catalog change. Again, this is the DBA best practice part of the section. I'm not going to spend all the time about loading, but I am going to talk a bit about this. Do a quick example here. I want to do a quick demo to show you this. Whoops. I've created a database on a small fast track system. Actually, it's a rather big fast track system. It's not this one over here. It's the DL980. This is 8-socket system. It's huge, but it's big. So anyways, quick example here. I'm going to create all my tables. I've already created the database, so you don't have to sit and watch that all run. However, I create all my tables, and then the 4 steps I showed you. The first step is doing just a basic load. I've got all my BCP commands, my bulk copy commands. I could paste those simply in there. Ultimately, those runs, now I could be pushing all these in parallel into multiple terabytes of data, pumping each one of those files in parallel into one heap table. In this example, I just pasted them all in because it's reasonably small to run in a minute here. The next step after that finishes, again, is the insert select. This is where we avoid all of our sorting, and we're just doing insert selects. Now the trick is we've got tab locks in each of these tables, insert selects with tab locks, with simple recovery mode for SQL Fast Track. Will create minimal logging, so you're not going to write tons of information into the log. As well as, you see, the data has been filtered for each table by partition. This matches the partition by date. So this example here, I'm using line item. This is a TPCH table. Maybe many of you might be familiar with it. I've partitioned it by year, and I can insert it in there and just filter it with my insert selects. There's no sort that's happening. It doesn't take hardly any memory because it's just smacking the data right in there. And the last step is to build these clustered indexes. Now the key to doing this is 2 things. When you build a clustered index, this system having 32 cores, if I was running everything in parallel, it's going to write 32 threads to build that clustered index. So it's writing, it's going to read, it's going to write 32 threads at the same time. When it's throwing those threads down for a clustered index, which is basically sorted data, it's going to start fragmenting the data again. To avoid that, you limit the amount of parallelism for each of those processes. In this example, we set our max stop 8 settings, so there's only 8 threads. Our testing showed that 8 threads of parallelism is enough to keep fragmentation down to good performance levels. So building this section, we're good to go. Did I run this already? Okay. And the last final step is just partition switching. Now, if you've worked with SQL Server best practices, we often call this the the window slide windows, partition window process. It's been a best practice used for a long time of partition switching. You don't have to actually insert data into your final table. You can just switch partitions in. This is a quick example of our load process, of a migration load process. Obviously, it's a much more complicated one than most of your load processes might be. Your data-to-data load processes wouldn't be that. Day-to-day, you might have just simple sequential data. We're loading data every day, and it's going into a table. It's partitioned. It's straight. It's simple. As long as you're throwing in the most recent partition and it's coming in sequentially, it's not volatile. This is a non-volatile load. Then you don't have anything to worry about. You just throw it in there. It won't fragment. You won't get bad performance out of it ever. It'll just stay consistent. Different example, if it works here, is the volatile incremental load. For this example, we'd use 2 different file groups, our volatile file group, which I'm calling the current file group, and the non-volatile file group, which I'm calling the historical file group. This is where I got fragmented data to non-fragmented data. I can throw a table in there, or a couple tables in here. I've got my big partition table, primary partition clustered CI table, and then my 2 extra small holding tables, which effectively, when I throw a view over it, becomes one table. So essentially, I've got fragmented data and unfragmented data, and they're in the same table, logically speaking, because they're under the same view, actually. And then I can beat the heck out of this file group, this current file group, updating, inserting, deleting, do whatever you need to do. Once that data becomes less volatile, you put it into the final file group, and you don't have to worry about it again. It's sequential, it's clean, and it goes untouched, or mostly untouched. You don't have to update that data. So for a good example, it might be maybe 3 months old data. You don't have to change that anymore. Simple step, like I said, you do bulk insert into those tables. Then you just manage the partitions later. So as your data gets old, you move it across, get into your final historical table. Again, I spoke about fragmentation. Quick thing you can take home is a way to check fragmentation. Right here, I have a query, DMV, that looks at fragmentation of your tables. So specifically, you would look at your large tables. Think of your large fact tables, several hundred gigabytes in size, over 50 gigabytes in size, maybe over 100 gigabytes in size, up to however many terabytes. You want to keep your fragment size down, your fragment size up, your amount of fragments down. This example here, the key number we're looking at is average fragment size in pages being over 500 pages. Now, if you go home right now and you've got a database and you run this same query, you're going to see it's probably going to say 8, because a typical SQL Server installation doesn't do large extents, doesn't write the data down as efficiently. So something you should write down here, which I don't have in the slide, is, and I think Jim will actually be talking about it later, the data warehouse best practice for Fast Track is the 2 startup parameters, SQL Server startup parameters, -E and -T1117. -E makes sure that it makes SQL use large extents. So when it extends and grabs out extra space, it grabs out larger extents or more extents. -1117 makes you write the data evenly across multiple files. Jim will explain a little bit more about that. If you don't use that 400 is always going to be like 8, basically. So a quick example, here's the query run. You can see in the six column over, average fragment size in pages of my table here, 450, 460 area. If you're getting in the 300 range, you can still get decent performance. It'll start to deteriorate. Anything below that, you're getting significant random I/O, and this system's not really optimized what Fast Track requests that you optimize. What we would suggest for SQL Server data warehousing, you're definitely not optimized. Following the load instructions, the load best practices that I just went through in detail, are how you get there. This is what we're actually aiming for. Quick example, this is a quick picture of a Fast Track system. CPU is on the left, or on your left, and your disk on the right. The goal of Fast Track is balancing CPU to disk, ultimately, from the right end to the left end. Any parts of that, the HBA cards, the fiber switch, or not necessarily fiber switch, but any switch, the storage processors, if any part of those are insufficient, that becomes your bottleneck. Doesn't matter how much disk you have if you don't have enough HBA cards to handle that bandwidth. That's what our reference architectures do. We've tested these systems with specific workloads and actually made sure that there are no bottlenecks. Let's get on to the next piece here. Now, how do we balance the two? Well, CPU I/O is easy. Disks can go a certain speed, right? They can 10K disks read a certain speed, 15 disks read a certain speed. That's easy to start with. But how fast can a CPU process that data? Well, we've come up with a measurement we call maximum consumption rate, which is based on SQL Server's maximum consumption rate. What an actual core can do. So different cores could consume differently. Obviously, a 3.3 gigahertz core can consume much more than a 2.2 gigahertz core. You multiply that by the amount of cores in the system, so you might have 8 cores in a system that are 2.2 gigahertz. You'll have a certain MCR rating for each of those cores. Aggregate, you'll have the entire rating for that entire system. So this is how we standardize our calculations to build that balance from CPU to disk. Quick demo. I'm going to give you a little show of that again. To test our MCR rating, I've got a quick query. This query, don't worry, I will give you all these files and there's all this code for your use later. This query is just a simple aggregation based on a line item table. The key to it is it's all coming from memory. It's not coming from disk. It's isolating what these CPUs can do. So, and I do a couple settings, set statistics I/O on, set time I/O on. As long as I've got those on, it's going to spit back some statistics that I need to see what kind of performance these disks do. You can see down below I've actually run this query. It just takes about 6 seconds. So I'll go ahead and run it again. Whoops. Wrong database. There we go. Sorry. I missed it. Now we got it. Takes about 6 seconds to run. However, the key to this query is that it doesn't actually read any disk. This will tell me how much it reads. I apologize for the size of these prints here, but this set statistics IO on will tell you the logical reads, the physical reads, the read aheads of that query had to do when it ran. For checking the MCR, again, like I said, we're not using the disk, we're not pushing the disk, so we actually check. Really, this should only show logical reads, and then this example does. It just shows logical reads. There's no physical reads. I'll do a quick piece of this demo here. Here's a quick example of the results. Notice I've highlighted the key numbers in it. The formula down at the bottom is what we use to calculate the consumption rate of a CPU. Logical reads divided by the CPU time, obviously in seconds. Multiply that by the amount of pages, because logical reads are the number we get are in pages. As you can see up at the top here, logical reads 499666. That's in pages, divided by the CPU. So our calculation down here, you can see it in the formula at the bottom. I've plugged those two numbers in. Obviously divided the 18017 by 1,000 because it was milliseconds. And I got 216 megabytes per second. These cores on this particular machine, now this is an old fast track machine. Don't make any comments of that, because this is the newer machines. Actually, the new reference architectures have much more powerful CPUs. We're getting about 300 megabytes per second for some of the new Intel cores. This machine has 216 megabytes per second consumption rate for those CPUs. Thus, with 32 CPUs, you can do the math. 32 times 216, that is our total consumption rate of that machine. So we have to turn around and say, okay, we need this much I/O from the disk. This is the amount of disk that we need. This is the amount of LUNs that we need. We've got to build storage and I/O and the switch that actually can pump that across and make sure it's a full balanced system. We'll switch back over here. Whoops. Did I get it? Got it. Okay, again, end to end. We got the right disk. Then we get to pick the amount of RAID 10 LUNs over there on the right that we need to feed those disks. Now it doesn't have to be RAID 10 LUNs. Our HP system is actually excellent at RAID 10, so we use RAID 10 LUNs to get the balance. Now, how do we measure actual I/O? We can't just take the disk ratings, right? We have to actually get what the actual performance, what SQL Server can do. So we need SQL type of I/O, which is definitely different than just a regular scan on a file on a disk. So we use SQL I/O. I know maybe some of you might have used it before. Has anyone used SQL I/O before? Okay, so some performance guys out here. It's not the best tool in the world, but we isolate it, make sure we use it for just specific purposes, doing small requests, try to get sequential reads. We use this, we run this simple tool, and we can get the expected performance of what that system could do with SQL Server type of I/O. But that's not good enough, right? Obviously, real-world workloads aren't tools. They're not benchmarking, executables. They're actually, I'll skip past that SQL I/O test, because all this is just running the SQL I/O. We have to use actual workloads, which we've done. We've built actual workload, data warehouse workload, to actually test this data. And we actually test on every system that we test. We build these reference architectures using this specific workload with specific levels of concurrency, with specific, various types of queries. But with these specific queries, the same ones every time. We can build this on any system at various sizes, depending on the system, to get actual real workload tests and to really test that throughput. That's what the reference architectures do for you. They've done all the work. It's configuration. It's bill of materials. It's best practices. It's from end to end. You're ready to go. You have a data warehouse. You have a business use case. You have data. This provides you everything else. Obviously, you need a couple guys to fire off the queries, but maybe carry over your servers. That's how Fast Track works for you. And again, some of our metrics here. The throughput metrics, ultimately, I gave you the MCR ratings. Ultimately, like I said, 216 megabytes per second times the number of cores. That's the high water mark of what that system can actually do. Now, in reality, with lots of concurrency, lots of different activities, you can't use that 216 megabytes per second constantly because there's constantly switching of queries. The example I gave you was best case with one query. So with the full workload, with all the activity, the throughput metrics that we've rated these systems on actually turns out to be around 80%. It's at least 80% of the baseline rates of what that actual system's hardware can do when it's put into real workload, query workload situations. So I think that's the end of mine. I want to push over to Jim, who's going to talk a little bit more about HP and about specific hardware that's available right now. Jim, you want to come on up here? Thank you, everybody.
All right, thanks, Mike. Just before I start, I want to mention that we're going to have some questions at the end. I'm going to save about 10 minutes at the end, so please hold your questions till the end, and we're also going to go away some free giveaways here, too, if you hang on for that. So, my name is Jim Holler from HP. I've been working with Mike and his team for several years now in the Fast Track configurations. So what I'm going to talk about today is kind of expand on what Mike talked about and talk more about the new features of v3.0. This is our third iteration of Fast Track. So there are some new features that are different from previous versions, and I want to kind of highlight those, as well as talk about some of the best practices that we've derived from the testing that was involved in developing those reference configurations. So what's new basically boils down to it's all around the hardware. So as the hardware gets faster, as memory gets faster and more capacity, and CPUs get faster, storage arrays get faster, we have to adjust our configurations. We have to adjust our best practices because things start to crop up. Things have to be adjusted just to keep up with the demands that all that hardware places on the configuration. So a lot of these things that I'll talk about are a direct result of increased capacity in hardware, and as we test these configurations. So here's kind of a highlight of the new features. Towards the top here we have new memory guidelines. Now in the past we've kind of had a kind of recommendation of 4 gig per core for memory. But now as we have disparate cores between AMD, 12 cores, Intel 6 cores, et cetera, it becomes harder and harder to tie a specific figure to a CPU core. So as Mike said, the MCR becomes more and more important because individual CPUs vary as well in the same Intel or AMD family, gigahertz rating, they all factor in there. So the memory guidelines for Fast Track 3.0 are actually tied to the configurations themselves. So we tested various options. For example, the 2-socket configuration, 2-CPU configuration, has 96 gig of memory. So we've tested 128, we tested 48, we tested 64, and came out with a sweet spot of 96. So that's the memory configuration for the 2-CPU configuration. And we have another one for the 4 and the 8 sockets. So they're all different, and they're all tied to a specific configuration and no longer tied to a CPU core. As Mike alluded, there was a few startup options, T1117 and -E. We've also tested a T834, which is a setting that allows the buffer pool, the SQL buffer pool, to lock pages in memory and use large pages. Now, we've had mixed results with this setting, so the takeaway here is that you should baseline this in your environment because some workloads you'll get a significant performance gain, while other workloads it'll be nil. So it's really, whatever your workload demands can take advantage of this feature. Another big thing in 3.0 is the storage configuration. Previously we used RAID 1, and now we're going to 4-disk RAID 10. So instead of 2-disk RAID 1, I'm going to 4-disk RAID 10. And the real factor there is not really performance or anything, it's really a management usability decision. So as you can see in this box right here with the 8 CPUs, 12 storage arrays, we're pushing upwards of 48 LUNs with RAID 10. Now if we would have stuck with RAID 1, all of a sudden we'll look at 96 LUNs. And if you ever set up a fast track system and if you have scripting and everything, it still takes quite a monumental task to map the drives, create the LUNs, mount them, load them. I mean, the more LUNs you have, the more management nightmare it becomes. So kind of saw the writing on the wall as everything gets faster and faster and have more capacity on the hardware side, that we don't want to be eventually trying to configure 300 or 400 LUNs on a system. So that was the decision there. We find that a 4-disk RAID 10 has about the same performance as two 2-disk RAID 1s. So there's no performance loss, no real performance gain, but you gain in all the manageability. Valuing fragmentation, we put more time and effort into the whole fragmentation, as you saw in Mike's fragmentation query. We now have a baseline where we can evaluate fragmentation. So when you get a system in, you can do a baseline as soon as you load it, and over time you can run queries on that fragmentation and see if it's going down. And if it keeps going down, you have to make a decision, hey, I got to revamp my load scenario. Do I partition a table and have that table do more updates than the other tables so I reduce my fragmentation on all the tables and just have one table or something? So it's a good way it's a good practice to evaluate that over time to see if that fragmentation is going down. Mike talked about the new load methodology. This is a very significant achievement as far as load-wise. For a 1 terabyte database, it was running about 20 hours, and now with the new load methodology, we're getting it down to about 10 hours, so it shaves it almost in half just by doing the different methodology, and we don't take any hidden fragmentation by doing that new method at all. MCR we talked about. And now the new reference configurations also include more hardware guidance and settings. So in the past, we've kind of did all the hardware settings, the memory, how much memory it has, here's the disk layout. Now we're adding more information around MCR for the CPU cores. We're adding information on I/O throughput, both logical, which is reading from cache, and physical, which is reading from the actual disks themselves. So as you evaluate these configurations, you can say, okay, this CPU has this MCR. Maybe if I buy a fast track system, do I need that fast of a CPU? Or you can evaluate, if you know the MCR of a particular CPU, you can figure out, how you can adjust. Or I don't always have to buy the fastest CPU, but in general, you want to be upwards in the top range of the CPUs because the performance is significant between the upper mid-range all the way down to the bottom. So architecture-wise, we talked about RAID 10. 8-gig storage arrays are huge. In the past, in Fast Track 2.0, we've been using 4-gig arrays, 4-gig HBAs, and now we essentially, theoretically doubled our throughput by going to 8-gig HBAs and 8-gig arrays, 8-gig fiber. So that takes a load off the storage side and enables to keep up a little bit with the CPU side. New load procedures we talked about. Highest clock speed. So we did a test back in 2.0 and tested CPUs all the way down from 1.9, I think, to 2.0 gigahertz, all the way up to the 3.1 gigahertz. And we found going from the bottom end to the upper tiers provided a huge increase in performance. But going from like the middle upper tier to the top tier provided only a marginal increase in performance. So takeaway there is buy the fastest CPU you can afford. Don't necessarily have to buy the fastest. You can get 90% of the performance by maybe coming down 1 or 2 levels off the top bin. P2000 arrays are new for Fast Track 3.0. They're just a new generation of MSA arrays. They're called the P2000 now. Nothing has changed there. The default settings are still valid for all Fast Track settings, so there's really nothing to do as there was in 2.0 as well. We currently have 5 configurations. We have AMD, we have Intel, 2-socket, 4-socket, and we have a single configuration here for the 980, which is Intel only. And the biggest thing that these allow you to do is kind of profile what a Fast Track system performance would look like given a tested configuration, which we've already tested, tweaked, and tuned. And that, along with some of the sizing tools that we have at HP, allow you to kind of fine-tune a configuration for your exact workload. These will take in all these metrics from your workload. You plug in all this information, how many queries per hour, what your query makeup look like. Are they complex? Are they CPU bound? Are they TempDB heavy? And that'll spit out a configuration. Because a lot of times, if you just take a configuration based on data warehouse size, it come back to bite you, because you may need 10 terabytes. So you buy a 10 terabyte configuration, but it doesn't have the CPU power to handle your workload. You may need the 580 configuration, which is a 4-socket system, just for the sheer CPU power that your workload provides, even though you don't need the storage. So that's something to keep in mind as you size these things. You cannot definitely not do it alone just by storage capacity. Hardware selection. We talked about, per core guidelines no longer apply for memory. That doesn't mean that additional memory may not help your workload. So we have a configuration for the 980 that says 512 gigabytes of memory. If you take your workload and put it on there, and it's very memory intensive, you can actually use that memory instead of spilling over to TempDB, and you might find some increased performance there. So it's really kind of a guideline that this configuration performs this way with this amount of memory. Now, it's up to you to kind of baseline that with your workload to find out that if additional memory might work. In some cases it will, some cases it won't. Consumption rates, as Mike talked about, we have the maximum consumption rate of the CPU, but we also have the benchmark consumption rate, which is also a consumption rate based on your workload. So the maximum MCR is what the CPU can do. The BCR is more of what the CPU can do under your workload. So that's another calculation, and that's it's slightly lower than the maximum calculation because it's actually running a particular workload. So what you want to do is match the BCR, ultimately match the BCR rates to what the storage can do, so that on your workload you're producing the maximum amount of throughput from your storage. So here's what the layout looks like for the LUNs on FastTrack 3.0. We've gone to RAID 10 for all the data LUNs, log LUNs. We now have a 6-disk RAID 5 for a secondary stage. You notice we have a primary stage, TempDB, and primary data are all striped on the primary LUNs. So data 1 through data 12 all contain TempDB, primary stage, and primary data. The secondary stage is mainly used kind of a landing zone, backup files, load files. It's a big place to load stuff that's local to the system. 2 log LUNs. It varies by configuration. This is the configuration for a 2-socket, 2 CPU configuration. Like the 980 has, I believe, 5 or 6 log LUNs, as well as 48 data LUNs. So it really scales on the size. The 980 also has 2 landing zones as well. But each array is pretty much configured identical except for the log or the stage, so that when we actually stripe the files, everything is the same. It writes the same. We use those T1117s and the -Es to make sure that every time something is written, it's written the same. So we take advantage of all those spindles that we have available. So I'll just give you an example here of the data striping with FastTrack. So you have an example of 4 LUNs here. These are 2-disk RAID 10, 4 pairs, and also a log LUN here. And basically what we do on these LUNs is we create the RAID sets, and then we have primary data and logs. And then we create a file group, and we lay down files over across all these LUNs. So each file group will have a data file in each LUN, so that when you write out to a file group, you're writing out to all those LUNs at the same time, and then you create multiple file groups. And the dual read and capability of the P2000 arrays will allow you to read multiple file groups, multiple LUNs, multiple files at the same time. So this takes maximum advantage of all the spindles you have in the system, since this is not, per se a spindle-rich type system. We don't have hundreds and hundreds of banks of disks to work with, so we want to make sure we take advantage of every single spindle we have on that system. Statistics and compression are some things that haven't really changed much. We're just kind of reiterating that for FastTrack 3.0. We still recommend them. We recommend to auto-update and create, because you don't have to maintain them that way. You set it to auto-update and create, And statistics are on a continuous basis, always updated and created. Composite statistics or multi-column statistics are critical for hash joins and loops and that type of thing. Because if you don't put those statistics on over time, it just it comes up with a bad query plan, and this really helps feed it to the right query plan. And then minimize manual stats on larger data sets. In larger data sets, there's more changes. Becomes harder and harder to maintain manual statistics on these larger sets, and it becomes a management hassle to always have to redo the stats or redo what columns you're going to report on if the columns change, that type of thing. Compression is still recommended. In current fast track guidelines, we're about 3 to 3.5 times compression. Now that figure is based on Microsoft kind of did a study in an average customer data set. Your compression may be at 2 or 1 or 4 or 5 or whatever. But this is just kind of a general guideline so that an average customer will have a 3x, 3.5x type compression. And the nice thing about compression, it helps reduce I/O requirements. So we're doing scans here. We're not doing a lot of indexing. We're just doing scanning in massive chunks of data. So if that chunk that we have to read is smaller, it's going to help increase your I/O performance. But again, if you have some random I/O there, it's going to decrease performance because you're constantly searching around, grabbing here and there, compressing, decompressing. So again, our overriding theme on Fast Track is no random I/O, or reduce it as much as you can. Sequential data scan, we talked about extend allocation. So all these settings are really to avoid fragmentation. Fragmentation is not your friend with Fast Track. So anything we can do, any options we set are all to minimize fragmentation. We're always going to have some fragmentation. But if we take these steps and put the -E, the T1117, pre-allocation of the database is recommended. So even though you're only using this currently, if you allocate out to here, anytime your database sizes and your database files get bigger and bigger, you're not spending time and fragmenting by allocating extra extents on those files, and that's a big factor right there, which minimizes the use of AutoGrow. So if you're pre-allocating up to the maximum level, you theoretically shouldn't use AutoGrow much at all, maybe on TempDB. We talked about memory guidance. QDEPs are another thing. These are all fiber channel based configurations, so we have QDEPs to work with. We've tested various settings of QDEPs. 48 to 64 seems to be the sweet spot, generally around 64 for most configurations. We have tried larger, and in some instances, going up to, say, 80 or larger might increase performance at some point, but it was pretty marginal when we did test it. So we found, 48 to 64 seems to be about the right size. RAID 10 arrays, management complexity, power settings. This may seem like a pretty trivial thing, but most servers ship today with BIOS settings that say balanced, balanced performance between power saving. Now, what you really want to do if you really want to extract maximum performance out of your system, it's a little performance, not a lot, but if you set those to max performance, that way there's no power saving stuff at all in there. It's just maximum performance at any given time. MPIO is another issue that has kind of reared its head with Fast Track 3.0. The 980 here has 48 LUNs, as we said. Each of those arrays, it has 12 arrays, 48 LUNs. So each of those arrays has 2 controllers with 4 ports. We have 9 HBAs in that system with 2 ports each. So we have 18 HBA ports. We have 4 storage ports times 12, so we have 48 storage ports. So the net is that we have about 3,000 different total paths that system can handle, and, well, not handle, actually. So if you turn on the default settings for the DSM for Windows, which we use, we don't have a custom DSM, we just use the Windows DSM. Round robin with subset is the default, and what that does is just reads in all these paths and just picks a primary and just says, okay, I'm going to use this guy, and if something happens, I'll start round robining through the paths of available paths to find a secondary. Problem is, MPIO is just overwhelmed with the amount of paths that it has to manage. When we did the 4-socket system, it wouldn't even boot once we turned round robin on with all those paths. So what we're doing for guidance for at least the 4-socket and the 8-socket systems now is kind of a manual mapping process. It's kind of a pain to do initially, but you only have to do it once. And what we use is the failover only policy for MPIO, which means you assign a primary path and 1 or 2 secondary paths for each LUN, and that way, if something happens, it doesn't have to think. It just says, okay, I just go to one of my secondaries. And that way MPIO is not stuck with the burden of trying to figure out all these different paths. There's a white paper out there that I wrote on how to set up that manual mapping. Again, it's a one-time deal, so it's painful up front, but it's really required for the larger configurations. Resource governor also plays a bigger role now. With the 2-socket configurations haven't really changed a lot with 3.0. It's really the 4 and the 8 where we run into issues with resources and allocation of resources. So the default setting without resource governor for memory is, I think, 25%. So any query can grab up to 25% of memory. So if you have 20, 40 queries running in your system, those are all going to try to grab 25% of the memory, which on this guy is 25% of 512 terabytes. So just I'm sorry, gigabytes. So it's still a huge amount of memory. So what we've done here is say, okay, let's take that 25% and bop it down to maybe 15 or 12 or 10 or something around there. And we found that makes a huge increase in performance for the 980, so the memory manager in SQL doesn't have to go out and constantly allocate, working set, deallocate, page in, page out, all that thing. So that was a big thing there. Again, we recommend 12 to 15 for the 980, but doesn't mean it's going to work in your workload. Again, you have to baseline that type of thing. But the takeaway is that you should definitely look at resource governor. Same thing with max DOP. This is kind of a resource governor for CPUs. If you use max DOP 0, which is the default, which is not doing anything with max DOP on the system, each query can try to run over all the CPUs. So you have 64 cores. Each query will try to run over all 64 cores. And then yada, 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 you have 20 or 40 cores, and all of a sudden, again, SQL has to manage all those CPU cores, and it just becomes a management nightmare for SQL, and performance degrades over time. Which brings me to a few other things that we found out with the 980. The current maximum size for a single fast track database, I think, is 64 terabytes, somewhere around there. So the DL90 is capable of 80 terabytes. So what we've had to do with the DL980 is kind of profile using 2 databases instead of 1. All the other systems use 1 database, but since we're looking at up to 80 terabytes, we're looking at now 40 and 40. And what we've done is modified our testing tool to read simultaneously over both databases and aggregate the throughput data. And with that set up, we've been able to get a little over 14 gigabytes a second, which is pretty impressive, less than 200 disk drives. Now, if you compare that to some of the big appliances out there, they have hundreds more disks on there, and they're getting about the same performance. So it's a pretty good achievement to get that amount of scan rate off of a 200 disks. So a little bit more about the testing. Mike talked about the testing methodology we have now. It's a little more formal now with HP and Microsoft. So before any vendor could just create a fast track system, test it or not test it, and just publish it and say, okay, here's a fast track configuration. So we wanted to make sure that if a fast track system is published, that it is actually tested and it meets guidelines, so that if you pick up that paper and buy all the hardware and set it up, you're going to get within that range of performance. So we have a formal sign-off process with HP and Microsoft now. And that's how, after we've optimally tuned the system. So we take baselines, we use our test tool, which has simulated workloads, mostly based on TPCH. It uses 5, 10, 20, and 40 queries in a simple fashion, which is a kind of a basic workload. And we also have 5, 10, 20, 40 for we call a medium workload, which is more CPU intensive, more sorts, more TempDB intensive, that type of thing. And then take all that data, aggregate it, and come up with some baseline numbers for that configuration. So it's a little more formal. It's we rely more on data than we did in the past, especially throughput data. So it gives you more information basically to make a decision. Some of the futures we're looking at. Right now we're looking at DR solutions for fast track. It's kind of a manual process right now, so we're not calling it HA. It's more of a DR solution. You actually have to do some tasks to manually fail over things. We're using things like snapshots, which are a core functionality of the P2000 arrays, allow you to replicate snapshots from one data center to the other. You can mount those snapshots and bring up a DR system, that type of thing. So the follow-on to that's going to be more an HA solution where we can kind of automate that whole process and have it not rely on any manual processes. Direct attached storage, a lot of customers have been asking about that. So we're looking at that, direct attached with storage shelves, switch SAS, all kinds of things there. HP blade system, a lot of customers like the blades, so we have two options with the blades. We have fiber channel, we have direct attached, so there are some options there. Solid state storage is probably one of the more interesting things here, mainly because the cost of solid state storage is starting to go down as the size of solid state disks go up. So as we're getting in the range of, say, 300, 600 gig solid state disks, they're becoming very attractive to maybe you work in the fast track and eventually work it into a whole solid state system. So that'd be pretty impressive. Other BI systems, looking at OLTP, SSIS right now, fast track is only for data warehouse, but evaluating other things, maybe like going forward to kind of expand out the whole BI platform. So to summarize everything, I should have some time left here. These FastTrack 3.0 data warehouse reference configurations provide performance at a low TCO. Now, I think when we started with FastTrack 1.0, we were at about $14,000 per terabyte. Now with FastTrack 3.0, we've come all the way down to around $5,000 or $6,000 per terabyte. So as the hardware gets more efficient, more faster, more capacity, the price kind of stays the same, which makes the price per terabyte come down quite significantly. Reference configurations, again, they're tested, they're certified. We've spent a lot of time certifying and tweaking and tuning all these configurations. So when you actually pick up one, you know that if you build it exactly as in the paper, you're going to get exactly that performance. Sequential scan, we can't say this enough. We've had a lot of customers say, okay, I bought a fast track system, I took my workload, and I just plunked it down in the fast track system. How come I'm not getting 10 gigabytes a second, if they have a random I/O type workload, a traditional workload, it's just not going to work well. If they have to have some modifications, unless you're a pure sequential scan type workload, you can't just put it on there without modifying. So I think that brings us up to questions. Yes?
I saw that you're experimenting with snapshotting for one of your high availability options. Have you experimented with that as a means of replicating, like as opposed to your staging model with the stage 1, stage 2 switch, where I could basically publish 3 instances globally of this FastTrack data warehouse?
Okay, so the question was, can I take the snapshot technology and use it kind of as a staging platform? So I,
To replicate data
yep,
to multiple database servers geographically distributed.
yep, you can do that. Right now it supports multiple snapshots to multiple sites. So you can take, you can set up replication between one or more sites for a particular LUN, and then that LUN, as you schedule it, will go out, it'll create a snapshot, and it'll replicate to each of those sites at the same time or on a schedule or whatever have you, so that you have not only one copy in a different site, you could have 1, 2, 3, however many you have. I'm not sure what the limit is, but it's a whole bunch.
One challenge I found with my organization is that typically my organization has made a huge investment in SAN technology that's not FastTrack.
Okay.
So culturally, there's a lot tied up in that huge investment. It's hard for people to get their minds around how this significantly less expensive piece of SAN technology could be so much more performant. I was wondering if you had any silver bullet responses to that way of
Okay. So the question is, if you compare fast track SAN technology to traditional SAN technology, Why is Fast Track so much faster than this old technology that's been around for a long time? It's performed very well, and everybody has it. Well, the answer is in all the steps we talked about in loading and make sure everything's sequential, make sure all the data files are written correctly, all the data files are striped. It's really in the methodology. You know, if you took a traditional data warehouse that you're running on your SAN right now and just put it on Fast Track, you wouldn't get the same performance. It would be pretty bad, right? Because you have a lot less spindles and using the same type workload. But if you modify that workload to use a sequential scan and take away some of your indexes and load it exactly as Fast Track dictates, you'll get really good performance. So it's really in the loading and the setup of how the data files are laid out and how they're striped and everything like that. Yes, another question?
Do you have customers that are trying out the solid state solution at all, and what performance boost have they seen? We have, in our data warehouse, we implemented a solid state drive for our TempDB.
Yep.
And found that a lot of queries and things are a lot faster. And I don't know what feedback you've gotten already on that.
Okay, so the question was, any customers evaluating solid state drives for SQL Server and SQL Server Fast Track yet? Yeah, the same experience that you have. A lot of people looking at it, TempDB, just experimenting. It's like, okay, just put my TempDB on there. And they're finding, yeah, there's a pretty good increase in performance in a lot of cases. So what we're looking at doing is not only using it for TempDB, looking at it for primary storage as well. So as these drives get larger and larger, you can say, okay, you know, it's not just for TempDB anymore. I could actually use this for primary storage. And, you know, how fast would that be? So, yeah, so there's a lot of interest. People are poking around with it a little bit and finding pretty good results. Another question?
You mentioned about power settings. You don't get something for nothing. What sort of increase in electricity price are you getting when you're putting it on maximum performance?
Right, so the question is related to the power settings and BIOS and control panel. If you do turn those on, you know, how much increase in power consumption is it going to be? I don't have any figures on that. It will be an increase because, yeah, you're going from balanced, where there is some, you know, power management involved, to no power management, just full power all the time. So I don't have any figures, but if it's valuable to you to get maximum performance, you kind of have to weigh that, you know, in yourself. You say, well, if it's a 10% increase, you know, maybe I run the server on max performance for a month. Maybe I run it on balanced and see how much more electricity it uses. And if it's worth it to you, turn it on. If not, you can just go back to default.
What have you seen as far as what it has done for you all?
As far as percentages?
Percentages? Do you have any percentages?
We don't have the percentages. We didn't document those percentages because it was really just more in the test process. We gained a little bit performance here. We're testing lots of things. So documented percentages improvement we don't have. However, once you have the system, you're capable of checking that yourself. Also to note, using this setup by balancing it, you're not adding tons and tons of extra storage. You're not needing that extra storage enclosure. So you might up your power settings for this enclosure. However, you're not buying 3 more enclosures at the same time. So you're getting the best bang for your buck out of the hardware that you're actually working with.
Yes. Yeah, we haven't done a lot with SSIS yet. It's kind of a fast track future. We want to, kind of move to that. Have you guys done any SSIS testing?
Not for fast track yet, no. But yeah, but obviously it's
on the
a
roadmap.
specific workload that's on the roadmap.
Yeah.
Again, fast track. The methodology for designing these reference architectures and these white papers kind of fits to every workload. We just define the next workload and move on to that one. So it's in the line to work down towards that.
Yes.
to do that same type of data movement. The practices can use it in the same way. I mean, what you describe is more like the hub and spoke type of architecture, right? So your hub's getting all of your aggregation, your big, meat grinder type work, and your data marks are getting all that other stuff. Exactly fits, and that's perfectly good for either of those load procedures or those queries that I described. In fact, they fit better towards it. Using that just one central data warehouse, you might have a little bit more of a mixed workload if you want to try to make your data warehouse your data mart as well. So separating that out makes it easier to do those types of queries and those practices.
Questions? Yes.
Yeah, the one piece I'm missing, and please come to me. How do you keep your data warehouse up to date? What tools do you use to get the net changes in?
Well, you can use any tool. This is regular SQL Server.
And at that point, you can use SSIS.
You can
Right.
absolutely,
Okay,
yes.
that's
Yes,
how
yeah, you can definitely use SSIS. As far as other specific testing of those workloads, you're right. You can absolutely use SSIS. Fast Track has a ISV partner, Awarescape, who makes an excellent tool for doing ETL, moving that data and querying stuff. There's plenty. Yes?
Are you talking about SSIS into your staging or into your production warehouse? Because I'm surprised to hear that, because all of my experience with SSIS has shown that it's much slower than this default insert.
Well, yeah. There is SSIS is very configurable. You can manage entire ETL or ELT type processes, right? So I would go into staging. Typical best practices are not to generally dump all your data right into your final table, for the reason that you might have to have some change data capture or some sort of transformation of the data that needs to happen on that system. So yes, so you would be able to do that and you can manage it through SSIS.
Really talking managing the ETL process with SSIS in staging, but then best practice is still bulk insert from staging to production.
Yes. Again, the whole point of the staging really is to isolate that area so it's not, what you do to it is not affecting the architecture, the fragmentation of what's on, the permanent data. So, exactly.
Yes.
If you want geographic copies of your warehouse for distribution across different continents, done any kind of geo-replication or using SSIS to parallel copy the data out?
Well, so the question is, if you're trying to distribute your data warehouse across data centers, across continents, geographic locations, you can use the built-in snapshot capability of each of the arrays. So you can create a single snapshot set, which is all the arrays, all the LUNs, etc., and just have them replicate to a specific place on a schedule or one time or however you like it. And that can make multiple copies of a single LUN or a single set of LUNs to go to multiple places. So you don't have to do one at a time. You can just tell it to send out and make multiple copies. Any other questions? Nope. All right. I think we have some giveaways here.
I want to add one more thing. All of the stuff we've discussed here is, I've heard it described once before, Fast Track, as being, it's a white paper that tells you the hardware to use, the configuration to use, and the best practices for your database for doing it. It is actually. The Fast Track reference guide, Fast Track 3.0 reference guide is available online. You search for Fast Track. All the stuff we've discussed in here is actually in this reference guide, as well as links on their websites to the actual reference architectures, where you can, pick out your system for you right there online. So, anyway, sorry. Go ahead and did you hand out your little?
All right.
All right. So we tossed some out.
All right. Thanks for coming.
Thank you.